Hello, class. Today we're going to do a little bit of review of trigonometry to set us up for success in our physics adventures. So again, this should just be a review, things you've come across in geometry or other courses that focus on trigonometry. So we're going to get to an example in just 1 second. But before we get rolling, I just want to talk about two different concepts here, which you probably have come across in the past. If you haven't, then here they are. If you have, then it's just a quick review. All right. So in math and in physics and science in general, we have two different types of numbers that we'll be using here. Those are scalars and vectors. Scalars are numbers or quantities or measurements that are represented how we usually think of as numbers, which means what I mean by that is that their quantities are represented by just a number. So if you give a number, and of course in physics we're talking about a number and a unit, if you give the number and a unit, and that fully encompasses a representation of that measurement or of that quantity that we're expressing. So some examples of that would be things like mass. So if we take your mass, you have some amount of mass in you, and that mass doesn't have any direction to it. And direction, a little bit of spoiler, has to do with vectors. So if we have a physical quantity that's represented by just a number and no direction to it, then we have is a scalar. So again, an example is mass. So because your mass has no direction. The same thing with your height, right? So your height from the bottom of your foot to the top of your head is going to be, let's say it's 5'5", all right? That doesn't matter which way you're oriented, right? If you're lying down, you're still 5'5". You're standing up, you're 5'5". If you're standing on your head, if you're doing a headstand, you're still 5'5", right? So your height doesn't have any direction to it. Your density doesn't have any direction. Speed doesn't have any direction. So all of those physical quantities are examples of scalars. So things can be represented by a number alone. And of course, in physics, we would also use a unit to help represent those numbers. That is different from a vector. A vector is something, a quantity or a number or a measurement that can be represented by both, that has to be represented by both a number and a direction. So all those examples of scalars didn't really have any direction to them, but if we think about some other things, something like weight. So what direction does your weight have? If you go to the doctor's office and the doctor says you're 150 pounds, what direction is your weight? Your weight, of course, is pulling you in a certain direction, right? It's always pulling you down, specifically towards the center of the earth. We'll talk about that when we talk about gravity, right? Same thing with velocity. If we think about velocity, velocity is different from speed, and we'll talk about this when we start talking about things in physics. But velocity differs from speed in that it is speed. You're going a certain speed or a certain quickness in one direction, but velocity includes that direction. And then there are many other things in physics we'll come across that are vectors. So they will be represented by both a number and a direction. So the direction will be important. Another one is force. So if you're pushing an object, that is going to cause something different to happen to it than if you're pulling on that object, even if the pushing and the pulling have the same quantity of that force. So for instance, if you're pushing with 15 units in one direction versus pulling in the opposite direction with the same 15 units, something different is going to happen to that object depending on whether you're pushing or pulling. All right, so direction matters for all those things that are examples. And last thing to say about this before we get rolling on our example problem is that essentially scalars we're going to represent with just a number, so we know how to represent those. Those we can represent algebraically. However, vectors we're going to have to deal with a little bit differently, because since they have a direction to them, that means that vectors are representing physical quantities that have more than one dimension. Often we're going to be dealing with them in 2 dimensions, and in order to do that, it's often useful to use a Cartesian plane, just like what I've got set up over here, to represent the vector as what is essentially an arrow coming out of the origin. And in order to analyze that, we're going to play around with triangles in relationship to that arrow. So let's play around with our example and let's see how all of that works. All right, so we're going to play around with some triangles in our example problem here. We won't use any units. We'll have like a basic trigonometry, pure math example, and then we'll build up from there, right? So we're playing around with some triangles. Remember, any day that you get to do math is a good day, right? Any day is a good day to be alive and to do some math. So we're going to play around with some math here. We have a vector or a line that starts at the origin and goes a distance of 15 units at an angle of 30 degrees above the positive x-axis. So in our typical Cartesian plane, the positive direction is usually to the right on the x-axis, and the positive direction in the y-axis is usually upward, right? So we are going to get rid of those things I just drew. So we're going to draw a line that goes a distance of 15 units at an angle 30 degree above the x-axis. I don't have to be terribly precise here because we're just going to eyeball it, but also I don't have it on our Cartesian coordinate plane here. I don't have any units laid out anyway, so it doesn't really matter how long I make the arrow, but I do want to make it at about 30 degrees above that x-axis. So we're going to pretend that I drew something that's about 30 degrees here, and then we're going to say that the length of this arrow is 15 units. You'll notice I didn't give an actual specific physical unit there. This is just 15 units. So this is, again, just a kind of a pure math problem, all right? So now what we can do from here is that this arrow we can take, and we know that its length is 15 units, but if we project it down onto the x-axis, we know that that arrow went over some amount of units on that x-axis. Forgive my arrow, my new red arrow, horizontal arrow, for not being very straight. And we know that that is going to be some units that went over on the x-axis. You can probably answer for me, should it be more than, less than, or equal to 15 units? Ponder that for a minute. And then we can do the same thing on the y-axis, right? We can take and we can project down or over onto that y-axis. Now, there is some amount of distance that arrow went upward from the origin up to the point where it ends in that y direction, right? So it ends at some point over there, and we can go up. And again, that's going to be some number of units over there. And what I asked you to ponder is, should that be more than, less than, or equal to 15 units? You, of course, already know the answer, which is that if we look in the x direction or in the y direction, the amount of distance of the arrow that this arrow will have covered is going to be less than 15 units, right? Because really what we're doing is, look, we are making a triangle, right? So the arrow itself is our hypotenuse, and then we've made a triangle with the x and the y distances. And then we made a second triangle over here, though that, of course, is the exact same as the first triangle. So really, we're just dealing with one triangle that we just have changed the orientation of in order to make the triangle going down from that hypotenuse or going up from that hypotenuse, using the x and the y-axis as the other side. All right, so let's take a look. Question A asked us to figure out how far over we went in the horizontal direction, right? So how far over did we go over here? So let us explore that. And in order to do that, we need to remember how we figure out things about triangles, right? And what is a really important mnemonic when it comes to triangles, right, is SOHCAHTOA. So we've got SOHCAHTOA. And of course, the S in so represents sine, and we'll be taking the sine of theta, which the theta is always the angle that we're looking at. Remember that SOHCAHTOA works for right triangles and right triangles only. So we've got a right triangle right here if we're looking at this triangle, or if we're looking at the top triangle that we made, we've got a right triangle right there, right? And so we can't use our right triangle, the 90-degree angle, as our theta. We have to use either the smaller side or the larger side, right? And right now, since we were given the 30 degrees, we're going to use this side as our theta. So we can use sine, or of course the other two trigonometric operators are cosine of theta and tan of theta, right? So our so up here deals with the sine of theta, and that's going to equal whatever O is over H. And as you remember from your math classes, O is opposite and H is our hypotenuse, right? So if we take the sine of this angle, the 30 degrees, then we're going to find the quotient of our opposite side, which is this guy, is the one that's opposite to the angle, right? Well, let's find the quotient of our opposite and our hypotenuse. So our opposite divided by our hypotenuse gives us our sine is equal to our sine of theta. And of course, we can use cosine as well. However, cosine, the little mnemonic that goes along with it is ca, so C-A-H. So rather than O over H, that is A over H. And that is adjacent divided by hypotenuse. And so we took a look at our opposite to our angle. So if we're using this angle of 30 degrees, our adjacent angle would be the one that is right next to that, or sorry, our adjacent side would be the one that's right next to that angle, right? So this would be our adjacent side. And then over here is our opposite side. And then again, over here was our hypotenuse, right? So when we take a look at this triangle we've made, we have the three sides, and the relationship between those sides and each other will give us the SOHCAHTOA, right? And then our last one, I'm just going to pop on here, tan theta equals O over A, and we've already introduced both those. That's our opposite over our adjacent, all right? And again, our theta here, we're always using a specific reference angle. In this case, we were using 30 degrees, but we could have just as likely have used this angle right here, which actually is 90 degrees minus theta, right? Or in our case, 60 degrees, since 90 degrees versus and minus 30 is 60 degrees. So that angle over there should be 60 degrees. And we can find all the sides based off that angle as well. However, we're not going to use that angle because we were given the 30 degrees. So all of that was probably just a really long refresher for something that you already knew. So we're going to put that SOHCAHTOA into practice here, right? So if we want to find this side down here, we want to figure out what that is relative to our triangle, right? So I'm just going to redraw this triangle over here so that it looks a little bit, so that we're not impeded by the X and the Y axis obscuring some things, all right? So again, we've got this is a right triangle. We know that this over here is 15 units. And we want to find what's going on with this X side over here. We also have this Y side, right? So, and finally, we know that our angle theta over here equals 30 degrees. So if we want to find, we're going to start off with our X side. So we're going to try to find how large this side of our triangle is. We know that our hypotenuse is 15 units, and our X side is what we would call our adjacent side because it is the one that's right next to our angle, right? And over here, we've got our Y, and that's going to be the opposite side because that's the one that's on the opposite side of the angle that we're using as our reference to find everything. Now, in order to figure out that side, we're going to need to use our SOHCAHTOA, right? So we've got our theta. We know theta equals 30 degrees. And we have our hypotenuse, right? We know that our H equals 15 units. I'm not going to write the units there. It's just the number 15. Good. And so we want to pick out which of our SOHCAHTOA, which of our three trigonometric operators, sine, cosine, or tangent, we can use to find our missing piece of information, which to get our X length of that triangle, we want to find our A, our adjacent side, right? If we take a look at our trigonometric operators, there is one that uses the theta, the H, the hypotenuse, and the A, the adjacent, and that's our cosine, right? So we're going to take cosine of theta equals adjacent over hypotenuse. Now, adjacent is what we want to find. So in order to get adjacent by itself, we'll multiply each side by the hypotenuse. If we do that on the right side, hypotenuse in the numerator cancels out with hypotenuse in the denominator. And then whatever we do on the right side, we're going to do on the left side. So I'm going to rewrite this starting with adjacent. So that was all that was left on that left side, but I'm now going to write that. Sorry, that was all that was left on the right side, but now I'm going to write it on the left side. And then that's going to equal what was left on the left side, which was H times cosine of theta. So now all we got to do is we got to plug in numbers here. So our hypotenuse is 15 units, 15, times cosine of our angle, which is 30 degrees. So I'm going to plug this into our calculator. And the one thing I want to be careful about is that remember that whenever you use your trigonometric operators, your calculator is going to have two different modes. Move this over here, right? So right now I am in degrees mode, but I could put it into radians mode, and on the calculator I have on the screen, you'll see there's a little radians next to the 354, rad, next to 354. That means it's in radians mode, all right? So 30 degrees are not radians. So if I use this calculator right now, and I said 15 times cosine of 30, I will get a number that looks like this. 2.3137. That is kind of small, right? So if we look back at our triangle over here, if my hypotenuse is 15 units and my adjacent side is my long side, right? I would probably expect that side to be much bigger than 2, probably a little bit more than 10, maybe like 11 or 12 units. So let's go back over to our calculator, and let's, instead of using the radians, I'm going to click the degrees button to get rid of the radians. And now I'm going to delete that. I'm going to multiply 15 times cosine of 30 again. And this time, since I'm in degrees mode, since there is no little radians on the bottom left-hand corner next to the 15, I know I'm in degrees mode. And now I have to treat that 30 inside the cosine as 30 degrees. And when I do that, look at that, it's 12.99. So I was off when I said in between 11 and 12. It's actually a little bit bigger than that. It's pretty close to 15. So that side over there is 12.99 units in length. Great. So now let's next work on our y side, because we know how far did the vector go over in the x direction. It went 12.99 units. Okay, so next let's find the length of our y side of our triangle, because that's how far up our triangle went in the y direction, right? And just as a quick reminder, we're using this triangle right here, the bottom one, but we could have just as likely been using this triangle as well. Remember, the length, the upward height of this triangle on the right side will be the same as the upward height of the triangle that we made on the left side of our hypotenuse, or of our arrow, our vector. So either triangle that we want to use will end up with the same result on each side. All right, for the y and for the x. So we have our hypotenuse. We know that our hypotenuse is 15 units in length. We again know our theta, our angle is 30 degrees. And finally, now we want to find our y side, and that is our opposite side. So I'm going to represent that with an O, and we don't know how many units that is. We do know that our adjacent side was 12.99 units. We don't know what our opposite side is just yet. So honestly, we have another piece of information, right? We have our adjacent. We can use our adjacent over here as well, because we know 12.99. So why don't we come up with 2 ways to solve for our opposite side? We'll first use our SOHCAHTOA, and then secondly, we'll use our Pythagorean theorem. Okay, so let's table our adjacent side for now. Let's pretend we didn't know that. Let's pretend we were starting with our opposite side. And since we have our hypotenuse, our angle theta, and we want to find our opposite, we need to find which of our trigonometric operators from SOHCAHTOA uses all 3 of those. And that would be our sine angle. So sine of theta equals our opposite side divided by our hypotenuse. And since we're looking to find our opposite side, let's do the same thing we did with our adjacent side. We'll multiply times our hypotenuse, and that will cancel out our hypotenuse on the right side there, leaving just our opposite side. And then whatever we do on the left side, on the right side, we have to do on the left side. So this tells us that our opposite side equals sine times the sine of our angle times our hypotenuse. Right, which is written a little bit funky. I wrote it funky because usually we put our constant in front of our trigonometric operator, sine of our theta. And we can plug in numbers from there. So this is 15 is the number that represents our hypotenuse, the length of our hypotenuse, times sine of 30 degrees. And again, when you plug this into the calculator, you just want to be sure to use the degrees mode to get the correct value for that trigonometric operator, for that sine operator. Or if you are remembering back to your sines, cosines, that sort of stuff, you may kind of already know offhand, without plugging this into the calculator, that sine 30 is actually 1/2. So we could represent it with 1/2 or 0.5. So if we take 0.5 times 15, we're going to end up with an opposite side of 7.5. So this guy over here, so our opposite side or our y side equals 7.5, and that's units, just generic units again, because we didn't use any specific metric or imperial units here. Okay, great. So that means that how far up did the vector go in the y direction? That's 7.5 units in the y direction, and then how far did it go over in the x direction was 12.99 units. Okay, so what this means is that if we use a physical quantity that is a vector, and that vector was 30 degrees above the the positive x-axis, we can find out how much that vector went in the y direction and how much it went in the x direction using trigonometry to break down that triangle into the two sides. All right, so we're going to practice this with some physical quantities in a second. Some of them might make a little bit more sense than others. And so in order to elucidate all this, in order to illustrate all this, we're going to use displacement or movement. All right, so we're going to use some amount of distance you go in a certain direction. We're going to break it up to how much you moved in either the north or south or in the west-east direction. All right, so we've already gone over in our summer work here that in physics, we have two different types of numbers we'll run into, two different types of physical quantities. We've got scalars that could be represented with just a number, and then we have vectors that could be represented, that have to be represented by both a number, a magnitude, and a direction. So which direction they're going. And so when we think about vectors, we're always going to represent them just like we did with our first example problem, which is a hypotenuse on a triangle on a coordinate plane. All right, so we're going to play around with that with our problem set here for our trigonometry review. And the most familiar vector that we'll run across, the one that is easiest to visualize and to conceptualize and to intuitively understand for us, will be that of what we call displacement. And displacement is just the distance between the start and end point whenever we make a motion. All right, so let's take a look at this problem and we'll kind of elucidate what I mean by that. All right, so you take a 2-day trek hiking directly north on day 1. So we have a little visual over here, and I'm going to redraw portions of that down here. So on day 1, we go directly to the north, right? We're going to say this is to the north, right? And we're going to say that's day 1. I don't know why I wrote the 1 like a subscript. Day 1. All right, so I was going directly to the north. And then you set up camp for the night. On day 2, you hike directly to the east. All right, so I'm going to draw, and remember that usually our little cardinal coordinates, we've got north up, south down, and then going right is east and going left is west. So if we started, here is our start point here at the beginning of day 1, and then we ended day 1 right here. We set up camp. That's where we camped. And then starting from there, on day 2, we went directly east. So now I'm going to go to the east some amount, and we'll call that day 2. Again, I don't know why I wrote that as a subscript. Day 2. All right. So, and then just like we've got in our little picture or diagram over there, our graphical diagram, we know that by the end of day 2, we ended up somewhere. So we can call that our end point, where we got to at the end of day 2. And that's going to be some distance away from where we started. And we can visualize that distance with an arrow. I'm going to draw this one. Confusingly, I'm going to draw in my diagram. It's the dashed arrow is our overall distance. And then obviously in the original graph I made, the dashed arrows were the individual day 1 and day 2 distances. But don't worry about that. So this distance, this total distance, is our total displacement over here. This is our total. And our total, it sounds like, I'm not sure how we figured this out, because you probably have a better bearing on how far you went on day 1 and day 2 than the total overall distance. But in this problem, what I gave you is that end point was 17.0 meters. So this is 17.0 meters away from the initial start point. And we know that that endpoint lies 30 degrees north of east from your starting point. So what that means is that if we think about our starting point, there is the direction east away from it, and then 30 degrees up from that, 30 degrees up from that is 30 degrees north of east. So our angle right here, if we were to have a little coordinate plane right here, this angle is 30 degrees. And as we know from our work with triangles, we made a triangle right here, right? And that guy, the angle next to that 30 degrees will be 60 degrees. I'm going to erase that because we might use that triangle, but we're going to stick with this 30 degrees for now, right? And furthermore, in that same triangle, this opposite side, that will be 30 degrees as well, right? So there's a 30 degrees there, and then again, we know there's a 60 degrees right there, but I'm going to get rid of that right now just to simplify things real quick. All right. So what we're trying to do with this problem is we know our total displacement, the total distance we went was 17 meters, and we know the angle of our endpoint away from our start point. But what we don't know is how far did we go during day one and how far did we go during day two. So let's find that out just like we did with the example problem, right? So day two is if we use this angle right here, our 30 degrees. Let's start with day one. So day one is our opposite side, right? And remember from SOHCAHTOA, that it is sine of our angle equals the opposite over the hypotenuse, right? Sine equals opposite over hypotenuse. So we're going to use our sine, and that means that the sine of our angle, which is 30 degrees, right, equals our opposite, which is day one, that's what we're trying to find, divided by our total, or our hypotenuse, which we know is 17 meters. So we could plug in for our hypotenuse, 17.0 meters. Right, and then to solve for day one, we'll multiply each side by 17, multiply this by 17 meters, and that cancels out the 17 on the right side, and then we have to got to do that on the left side, right? So day one equals 17 meters, or sorry, 17 kilometers. I've been saying meters this whole time, but obviously we went further if we were hiking for 2 full days, right? So 17 kilometers times the sine of 30 degrees. We could plug this into the calculator if we wanted, but just remember that sine of 30 is actually 1/2. So this is 17 kilometers times 1/2, and that is going to equal 8.5 kilometers. So for day one, we went 8.5 kilometers. Now, that is the distance that we went on day one, all right? If we want to make this a vector, meaning give both a magnitude and a direction, right? And the vector version of distance is displacement. Don't worry about that. We're going to talk about that in our first unit when we start talking physics proper. Then we would want to add to make this a vector, we would want to add the direction that we went. And on day one, we know that we went north on day one, so we'll just add a little north there. And you'll notice that matches up with the answer that's provided on our problem set here. All right. So then let's also get day two, right? So day two now. Day two is our adjacent side. So day two right here is our adjacent side to this angle of 30 degrees, right? So in order to use that, we know that cosine of our angle equals our adjacent over our hypotenuse. So now we use our cosine of 30 degrees equals adjacent, which is how far we went on day two. I'm just calling it day two right now, divided by our hypotenuse, which again, our hypotenuse is 17.0 kilometers. So day two's distance will equal 17.0 kilometers times cosine of 30 degrees. And although sine of 30 is nice and easy, it's 1/2, cosine of 30 is a little less easy. As a fraction, it's the square root of 3 over 2, right? But we probably aren't going to do that in our heads, and then we'll have to multiply that by 17, right? So let's just bring up our calculator for that. So we've got cosine of 30. We're going to multiply that times 17. And remember, just make sure that your calculator is in the degrees mode rather than the radians. You'll get a different answer for each, but we were given our angle of our triangle in degrees. So if we're putting in 30, we want to put in 30 in the degrees mode, right? So cosine of 30 times 17 will get us 14.72. So this equals 14.72 kilometers for day 2. And of course, if we think back to our initial measurement had 3 sig figs, so we can round that down to 14.7 kilometers. And that, if we're thinking direction, was going directly to the east. So that is for day 2. And look at that. That matches up with the answer that I put in our problem set. So great. Again, we're just doing simple trigonometry using our SOHCAHTOA to figure out the sides of our triangle when we know one of the angles and we know the hypotenuse of the right triangle that we're making out of our distance we moved in day 1, day 2, and then the overall total distance we had. Question 2, you are driving to your friend's house. They live 22.5 kilometers away from you, and they are at a bearing that for some reason, you know the bearing, they are away from you, and it's 42 degrees. 42 degrees, and that bearing is west of south. So again, if we start south, right, so wherever our initial position was, this is our start, right, is right here. Start is right there. If we start south, we want to go west of that, and so that's 42 degrees. So if we make a triangle right here, that angle is what is our 42 degree angle, right? Okay, and then we want to figure out how far south did we go to get to them and how far west did we go. So we went some amount of distance south, right? South, right? And then we went some amount of distance over to the west. All right, so we can figure out how much south we went and how west we went. And to do that, we made, 2 triangles. We could have also made our sides of the triangle right here, right? This would also be west, and we could make the side of the triangle over here south. Those all are going to be the exact same sides as the ones that are opposite to them that I already made with this guy and this guy, right? So it doesn't matter where we place those sides, it just matters the one that's vertical is our southern distance, and then the one that is horizontal is our western distance, right? So let's work with our south first, all right? And to do that, I'm going to use this triangle that we made up here. All right, and then we'll use the other triangle, the bottom one, for west. But remember, they're the same triangle, right? So we'll use this triangle right here, and this guy has an angle right here that is 42 degrees subtracted from 90, right? So this is going to be 48 degrees right here. And then, of course, this angle right here is the same as that original angle we were working with. That's 42 degrees. So we can use either one of those to find our southern side here, right? And so if we go and look at SOHCAHTOA, we have 2 options. We can use our sine of our angle or our cosine of our angle. It doesn't matter which one we use. I'm going to use the 42 degrees since that's what we were given, okay? So at 42 degrees, since that's the bearing that we were given, right, then south is our adjacent side. And so we want to use our cosine, right? So our cosine of our angle equals the southern side divided by the hypotenuse. And then if we want to find the southern side, then our southern side is going to equal our hypotenuse, or our total distance, times the cosine of our angle, right? And our hypotenuse was 22.5 kilometers, right? We know that the distance of that hypotenuse. And then we multiply that times cosine of our angle, which again, we're using that 42 degree angle. And so if we plug that into our calculator, then we will find 22.5 times cosine of 42 will get us 16.7207, 16.7 kilometers. And that is our distance. So we went in a southward direction. So that's our southward distance, right? So that is how far down we went south from our original starting point to get to our end point right here, right? Now let's find our western side. So for our western side, we've got this guy right here. We're going to try to find this guy. And so we're going to use this triangle right here. And based on that triangle, if our 42 degrees is where we start with, then our western side is our opposite side, right? So now we want to use our sine of theta. So sine of theta equals opposite over hypotenuse. Or we could call that our west is our opposite side and our hypotenuse is just our hypotenuse. I'll just keep that as hype. Okay, so then if we want to figure out our western side, we're going to take our hypotenuse and we're going to multiply that times sine of theta. And so our 22.5 kilometers is the distance of our hypotenuse times sine of our angle. And again, we're using 42 degrees there. And so let's figure out what that is by plugging it into the calculator. We take 22.5 times the sine of 42 degrees, and we get 15.055 or 15.1 kilometers, which just happens to be the answer on our answer key. Great. We did a few problems where we knew the angle and our overall distance, and then we had to figure out how far we went in the first leg of our journey and the second leg of our journey. Now we're going to do the opposite. So now we're going to take and know what we did in the first leg of our journey and the second leg of our journey, and we got to figure out what our overall distance or our hypotenuse looks like and what angle that makes. All right, so let's try this with a purely mathematical example, and then we'll do some practice problems with actual distances and displacements. All right, so two vectors are added together. One goes straight up along the y-axis for 9 units. The second goes straight along the x-axis for 12 units. Draw the new vector that results from adding these two vectors together and determine what is the length of the new vector and what angle does the new vector make with the x-axis. So what we'll do, okay, now that I added a little coordinate plane in here, now we can play around with our vectors. All right. So we're going to throw two vectors on here. Okay. So there's one that goes straight up along the the y-axis. So we're going to say that the origin is our point where we started at. Right, and then we want to figure out where we're going to end. So one of our vectors goes straight up along the y-axis for 9 units. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm going to make a a vector that goes straight up along our x-axis, our y-axis for 9 units. All right, so it goes straight up, and that's our first vector. All right. And then there's a second one that goes straight along the x-axis for 12 units. So same thing. We're going to make a little 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I know those weren't terribly regular. Actually, I'm going to redraw those a little bit. I'm going to redraw those. We got one. And the second vector goes straight along the x-axis for 12 units. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. None of those are terribly regular, but yeah, get the gist. So we've got a vector that goes straight along and that x-axis in a positive direction. Cool. So there's a couple different ways that we can combine vectors. The first is we can draw them both along the x and the y-axis, and then we can figure out, well, where do they meet? So if we draw a little horizontal line from the top of the y-axis vector, and then a vertical line from the top of or from the furthest end of the x-axis vector, then they're going to meet at some point. And that some point is right there, and that is our end point. Another way to do this is, I'm going to switch colors, is it, so we had one that goes along the y-axis. We could just take, and wherever we started with that one, we could start our new one. So then we said that there was a second vector that goes straight along the x-axis for 12 units. And we know that if we went straight along the x-axis, we would just be going horizontally over for 12 units, and that would get us to the exact same point. Right? Or if we wanted to do it a third different way, we could do kind of the same thing we just did with two vectors. The tip of one vector starts the tail of the next one, but we could just start with our horizontal vector first. So if we start with our horizontal vector, This guy starts out with 12 units going over to the right. And if we start there, the tail of our next vector, that one goes straight up. That will again get us back to the same point if we go straight up 9 points. Right. So no matter what, we are ending up with creating an endpoint that's right here and a starting point that's right here. So our overall displacement went from our start to our end, and this is our total displacement right here. That hypotenuse that gets made from whichever triangle, either our top triangle or our bottom triangle, whichever one that we want to use as our basis for this this addition of vectors. Right. So we're trying to get this guy's length. So we want to figure out the length of that new vector, and we want to know the angle. What angle does it make? So either this angle or this angle right here. Technically, there are two different angles, so I'm going to call one of them theta, which is what we usually use for angles. I'm going to call the other one alpha, just because it might be a different angle, and so we don't want to use the exact same Greek letter symbol for an angle if it has a different value than the first angle. So let me pretty this up a little bit. So it doesn't really matter which of the triangles we use. Let's we're going to use this bottom triangle. Okay, so we'll use this bottom triangle, and again, it doesn't matter because no matter what, the sides of the triangle are all going to be the same length, right? Whether we use that bottom triangle or the top one, we're going to end up with the same length. They'll just kind of the sides will be swapped, right? So we know that we went straight along the x-axis for 12 units. So I'm going to give a number to this bottom side because that's the one along the x-axis. I'm going to put a number there, 12, and then the one that's vertical, the y-axis one, I'm going to give a number of 9. All right, so a magnitude of 9. All right, and then what we want to do is we want to find the length of the new vector. So we've got 9 and we've got 12, and we want to figure out what is our hypotenuse vector here, right? What's the length? Because that's going to be the length of that vector, that total vector in the end. So we can use our Pythagorean theorem, right? We know that a squared plus b squared equals c squared. And in this case, it doesn't matter which one we use as A. I'm going to use 9 as our A and then 12 as our B. And then obviously that means that our total, our overall end vector is going to be C, right? So we've got 9 squared plus 12 squared equals our total. No, don't solve that. Our total squared. 9 squared is 81, plus 12 squared is 144. That's going to equal our total squared. I'm just going to swap these. All right, stop trying to solve things, Siri. T squared can equal whatever 81 plus 144 is. So that's going to be 225. So if we take the square root of each side over here, boop, so the square root of t squared is going to be t, and the square root of 225 should be, not 25, should be 15. And we'll plug into the calculator just to make sure that Mr. Sheehan's math is correct. So 225, the square root of that gets us 15. All right, cool. And obviously the fact that that's a whole number should give you, not pause, but should be interesting to you, right? And ultimately in the end, what we have here is a 3, 4, 5 triangle, right? It's just a larger version. It's a scaled up version of a 3, 4, 5 triangle, right? So the 9 is our 3 side. 3 times 3 gets you 9. 3 times 3. Our 12 is our 4 side because 4 times 3 gets you 12. And that means since 3, 4, 5, our hypotenuse would be 5 times 3 or 15. All right, so that's the length. And then on top of this, we also want to know what our angle over here is, right? So we were able to get away with our Pythagorean theorem to find the length of our vector in the end of our sum vector. But now to get our angle, we got to use our SOHCAHTOA again, right? And since we have all 3 sides of this triangle, we actually could use any of our trigonometric operators, right? We could use SO, CA, or TOA. We could use our sine, our cosine, or our tangent. But since we were given our 9 and our 12 to begin with, let's use our tangent, all right? So tangent of theta equals the opposite over the adjacent, right? Stop doing things. So tan of theta, we equal our opposite. And if this is our theta, then our opposite is 9, right? So 9. And then our adjacent our adjacent will be 12. 9 divided by 12. So this is going to equal 3 over 4, or 0.75. But again, to get our theta, we have to do, since we have a tan of theta, right? We have the tan operator acting on theta. We have to undo that by taking the inverse tangent, or the arctan. So that means that our 3/4, we have to do the same to tan, take our inverse tangent to, because whatever we do on one side, we got to do on the other side. So over on our left side, we end up with just just theta by itself, and then that should equal our inverse tan of 3/4. So let's figure that out. And if we go over to the calculator, we're going to take the inverse tan, so tan -1 of 3 divided by 4, and that'll give us 36.87 degrees. So our theta equals 36.87 degrees is theta. So this guy right here is 36.9, we'll call that degrees. And that means, of course, since this is a 90-degree angle, since we made a 90-degree triangle, then we can figure out the angle over here on the other side, right? And that'll be 90 minus 36.9. So that'll be 53.1 degrees. And obviously in this problem, this is basically a pure math triangle we're making here, right, on the coordinate plane. So we haven't applied any units here, and we're not talking about movement or any physical vectors. So this is how we would solve this with pure math, but we're going to solve it the exact same way with our physics. We're just going to, put the math into the context of some sort of a physical problem. So let's try those practice problems now. So practice problem 1, we're hiking from a park to a hot spring in the Rocky Mountains. On the first day, you hike 7.2 kilometers directly north. So let's make a vector for that, 7.2 kilometers directly to the north, before setting up camp to sleep for the night. So this was our start right here, start. And then we ended up camping right here. And then on day 2, you hike 9.6 kilometers directly west to arrive at the hot springs just before nightfall. And since I was a dodo head and drew this too far over to the right, we're just going to shift that over a little bit. And then we're going to figure out how to get back to how to draw again. Here we go. So now we can go over to the west. That I cleared a little bit more space to the west. So then we went to the west 9.6 kilometers. Cool. Over to the west. And then we ended up there. So that is our end. At that spot right there, right? So we want to figure out what the straight line distance is from the park to the hot springs. So our park at the start was some distance away from the hot springs at the end. So we can figure out that straight line distance. That'll be the distance here. I'm just call that our distance total. So our distance total, we equal our distance on day 1 plus our distance on day 2. But since these are vectors, and since there's a directional component to them, we can't just add 7.2 and 9.6. We have to treat this like we made a triangle, right? So in order to figure out our straight line distance, we know that a squared plus b squared equals c squared. And if I treat d1 as a squared, that's d1 squared, plus d2 is b squared, d2 squared, that equals c, which is our hypotenuse, which is d total. So d total squared. Right? So d total squared is going to equal d1 squared plus d2 squared. And then finally, before I even plug in numbers, let me just solve for d total. So right now it's being squared, so we're going to undo that square. And so we'll take the square root of d total squared, and that'll end up with being just d total. And that'll leave us with the square root of d1 squared plus d2 squared, which we can then plug in numbers, right? We know that d1 is 7.2 kilometers squared, 7.2 km squared, plus the distance of d2, which was 9.6 kilometers. We're going to square that. And then let's see what those numbers are. So 7.2 squared will be something like 50 maybe 51. 7.2 squared, 51.84. So this will equal square root of 51.84. And that was kilometers, but we squared those kilometers, right? So km squared plus whatever at 9.6 squared was. So just thinking through that out loud, 9 squared would be 81, right? And then 10 squared would be 100. This is a little over halfway from there. So let's call this, maybe this would be like 93 or something. 92.16. So 92.16. Again, that was kilometers, and those kilometers are squares. It's kilometers squared. So then if we add those two things together, oh, wow. We end up with a nice little number, with 143.00 kilometers squared. Right, let's make sure that I did that math correctly. So we're going to add 92.16 plus 51.84. Good, and that's 144. Oh my God, Sheen, what are you doing? So that is 144. Whoops. Kilometers squared. And then, of course, we're going to take the square root of that. And you may already notice that 144 is a very particular number. That is a square itself. Oops, sorry. 144, we want to take the square root of that. But 144 is 12 squared. So taking the square root of that will give us 12 itself, right? And so square root of 144 is 12. And the square root of kilometers squared is just kilometers in the end. So our total distance was 12 kilometers. For part B, we want to figure out our angle from our initial starting position, start, over to our end, right? So there, again, are a couple of ways we can do that. We can either start looking north and figure out how far west we go to get to that vector, that displacement from our start to our end point, or we can start looking west. Start looking west, and we can figure out how far north that is of our west bearing to get to our displacement that we ended up with. So let's start with our north, since I think that's how most of us would start over here. So if we go north, then some angle over to the west, right, is what that angle theta will be. And since we were given our D1 and our D2, let's use those two, our opposite and our adjacent angles, for which we would use our tan of theta equals our opposite divided by adjacent. And if this is our theta, then our opposite will be due to D2, and our adjacent will be D1. So D2 divided by D1. And then we can plug in some numbers over there. Our D2 is 9.6 kilometers, and our D1 was 7.2 kilometers. So we can plug that into our calculator. 9.6 divided by 7.2. Guess it's 1.33333. If we go around the numbers, it's actually 4 divided by 3 is our answer there. And then theta equals the inverse tangent of that 1.33333, or 4 over 3. Those are the same number, fraction versus decimal form. And if we take the inverse tangent of that, then we end up with 53.1301. 53.1301 degrees. Of course, since these are measurements that we're dealing with, and since our initial measurements were given in two significant figures, then we should round everything to 2 significant figures, which you'll notice is not what I gave you in the answer key. I gave you 3 sig figs, which is not what you should have given me, because if we're attending to significant figures and we want to round to the level of significant figures, that is the number of sig figs in our least precise measurement, which both of them had 2 sig figs. So we will round this to 53 degrees. And again, we started north, so this is starting from north. This is actually going west of that north measurement, so this is west of north. So this would be our 53.1, or really what we should have had is 53 degrees west of north. And then if we wanted to start from a different angle, so we could have, again, we could have started from our west, and then we could have gone north from there. So going north from there, and then I'll eventually get us back to our displacement vector, our total displacement vector. And so that will be a different angle. We can call that alpha, and alpha will be, look at this, we made a 90-degree angle right here, will be 90 degrees minus our theta. Right? So that should give us 90 degrees minus 53, which would be 37 degrees. And that would be north of west. Because again, we started west and then we went north of that. Great. So either of those answers would be acceptable. And of course, two sig figs would be optimal, not what I gave you in the answer key down here, because that's 3 sig figs, and that would not match with the level of precision from the measurements we were given in the question itself. Question 2 for part 2. Let's take a look at New York City. So New York City is set up like a grid, with each city block having a regular length. Regular meaning the same length each and every time. So a city block looks something like this. Oop, if I can draw. Let's see. Let's put that over here. All right, so a city block is going to look something like this. It's north-south direction, so its height is going to be 0.24 kilometers, and then its length is going to be 0.08 kilometers. So a city block basically looks like that, and the whole city is set up like a grid with a bunch of these going in each direction, and then the streets passing in between them, right? So then you got avenues and you got streets going in between them. So for New York City, we've got those lengths and those dimensions for each city block. And again, for the length in the north-south direction, so we're going to call this, I'm going to set up a variable. We're going to call this B for block. And a block in the north-south direction is going to equal 0.24 kilometers, or 240 meters. And then a block in the east-west direction is going to equal 0.08 kilometers. Those dimensions as we were given in the setup of our problem. Now you travel from your friend's apartment east by 12 blocks. So wherever we start is the apartment. And from that apartment, we went over to the east 12 blocks. I'm just going to make that an arbitrary length there because we'll figure out how far 12 blocks is in a second. And then we've traveled south. So after we got to that point, then we traveled south 17 blocks. So then we traveled south, which is downward, 17 blocks. So we're going to call this first leg of the journey D1, and then we'll call the second leg of the journey D2, just like we've been doing. I'm going to switch up colors, and we can make and here's our endpoint. This is Central Park, right? So this is the park right here. And we can make a little vector that shows our overall total displacement, which is from our starting point of the apartment over to our endpoint at the park. And we'll call that our D total, or total distance, total displacement from our start to our end point. Right? Now, let's get some numbers over there for these things. So D1, we know is D1 is when we're traveling east, and that is a length of 12 blocks. So that's 12 times the distance. Since this is going east, this is the blocks. Oops, sorry, rather than D. This is our blocks east-west, right? The length of each block east-west is what we want to multiply that 12 by, since we went 12 blocks in that direction. And so we're going to take 12 and multiply that times the length of every block that's in that east-west direction. So that's 12 times 0.08. And so that should be 0.96 kilometers. Let's make sure I ran those numbers right. So 12 times 0.08. 0.96 kilometers. Great. Okay. So, and then for D2, we ran in that north-south direction. right? So that's 17 blocks times the length of a block in a north-south direction. And so that's 17 times whatever that length of a north-south block is. And now we're not looking at the east-west blocks, we're looking at our north-south blocks, and each of those was a length of 0.024. So it's 17 times 0.24 kilometers. And I'm not going to try to do that in my head. Though if I were going to try to do that in my head, maybe I'd guesstimate 17. If I round up, it's about 20. So 2 times 0.24 would be about 0.48. And then times another 10, because 2 times 10 is 20, would get us to 4.8, right? So it could be a little bit less than that. So maybe something like 4.5 or 4.4. Let's find out. So 17 times 0.24, and that's 4.08. 4.08 kilometers. So my drawing over here was not very good to scale. So, but that's all right. We can't always trust the scales or the shapes of things, right? Because over here at D1 was only 0.96 kilometers, but D2 was a little over 4 times that length because it's 4.08 kilometers. So obviously, again, we're not to scale over here. The D2 should be much larger than our D1. So let's just redraw this real quick. So if we redraw this, our scale might look a little bit more like this, right? And I forgot a couple of things here. We know that first line is D1, and then this second line is D2, and that was 4.08 kilometers in length, that downward vector. And then our overall vector, our sum vector, is our d total, and that's that diagonal vector that connects our starting point to our ending point. Cool. So let's find the length for that, because that's what we're trying to do right here, is find the straight line distance between our friend's apartment and Central Park. Right? So let us do that. And of course, for that, what we're going to do is we're going to use Pythagorean theorem, right? So a squared plus b squared equals c squared for a right triangle, right? And it doesn't matter which one of D1 or D2 we make A or B, but remember that C is going to be our hypotenuse. So C will be D total. That's our hypotenuse over there. And that squared should equal A. We'll just call that D1 squared plus B. Let's call that D2 squared. So our D total, if I flip the size over there, D total should equal D1 squared plus D2 squared under a square root. All right, so if we plug in numbers for all that, we've got 0.96 kilometers squared plus 4.08 kilometers also squared. And if we plug that into our calculator, 0.96 squared plus 4.08 squared gives us 17.568. If we take the square root of that, that'll be about 4.198 or 4.2 kilometers is our straight line distance from our apartment over to our park. That is the length of our vector, our total displacement vector. So now let's take and let's find our angle for all of this. All right, so now for part B, what we want to do is we want to find the compass bearing for Central Park's entrance from our friend's apartment. So we're going to take, and if we start at our friend's apartment, let me get my little things back here. There we go. We want to find this angle, right? And this angle is going to tell us, well, so if we start off from east, how far down do we go from there, right? We also can find, if we start south, how far over we went from there. So let's start with the east one, and we can find the other one, and we'll compare our answers to the answers that I gave you, all right? So we're going to start with east. We're going to find this angle right here. So that's our theta we want to find. And again, we've got our SOHCAHTOA. In this case, let's use the lengths that were given to us, the distances that were given to us. That's D1 and then D2. D1 being the adjacent side, right? And then D2 being the opposite side. So if we're looking for adjacent and opposite, we want to use a trigonometric operator, the SOHCAHTOA, that uses the opposite and the adjacent, and that's our TOA, and that tells us the tan theta equals our opposite over our adjacent. In this case, our opposite was D2, and our adjacent was D1. So that's D2 over D1. And that means that our theta equals the inverse tan of D2 over D1. So let's take and plug some numbers in there. So we want our inverse tan of D2, and D2 is 4.08 kilometers, and our length of D1 divided by our length of D1, which is 0.96 kilometers. Those kilometers cancel out, leaving us with no units inside the inverse tangent, which is awesome because we don't want to have any units in there anyway. So we'll end up with whatever that is. And let's plug this into the calculator. 4 divided by 0.96 is going to be about 4. So 4.08 divided by 0.96, that'll be 4.25. And then we'll take the inverse tan of that. Inverse tan, that gives us 76.759. Or we could call that, we could round that up to 77 degrees. So this equals 77 degrees. And again, this is if we're going and we're starting east and then we're rotating down, right? So then we have to rotate south of that. So this is south of east. This is 77 degrees south of east. And then obviously we can start the other direction. So if we wanted to, we could start from south. That's the other important direction here. And for our vector, for our sum vector, we want to then go east of that by some angle, right? And that angle will be alpha, and alpha will be 90 degrees minus whatever we found for theta, which was, of course, 77 degrees. So 90 degrees minus 77 degrees, that should equal 13 degrees. And that would be, again, if we start from south and then we go east of that. So this is east of south, 13 degrees east of south. So both of those are the correct answer, just from one perspective or another. With number 3, things get a little bit more complicated because now, rather than having 2 legs of our journey, we're doing a 3-day hike. So we have 3 different legs of our journey. So let's graph this out first, and then we'll play around with the numbers, all right? So on day 1, we hike 13.4 kilometers north. So I'm going to draw an arrow north representing our first hike, and we'll draw that coming out of our starting point. Great. And then day 2 brings us to the west. So we do 7.8 kilometers to the west. So we'll go over to the westward direction. I won't draw this arrow as large as the first one since it's fewer kilometers. So we'll label the first one D1 for our distance on day 1, and label this second arrow D2 for our distance on day 2. And then finally on day 3, we're going to go to the north again for another 8.90 kilometers. So starting where day 2 ended, we'll go up north again, maybe something like that. And that'll be D3. So we went some distance on day 1 to the north, then some distance to the west on day 2 to the west, and then some distance on day 3, up to the north again. And overall, we can draw a vector going from our start to our end, and it would look something like this, right? However, we haven't talked about adding more than 2 vectors together, so let's undraw that for a second, and let's think about how this is going to look, okay? So essentially, to go from our start position to our end position, which I didn't label, end, we are going up vertically or northwards some distance, and then over to the left to the west some distance, right? Now, our northward distance is performed in two different legs of our journey, right? Because the first portion is that D1, and then that second portion is if we go and we draw that D3 over here, starting from where D1 ended, because remember on day 2, we didn't make any northward or southward distance. We didn't make any northward or southward movement, only directly to the west. So we're still starting from the same latitude that we were at when we finished day 1. And then we go northward by the amount that was D3. So that shows us how far north we went. If we add D1, which is our all northward movement, and D3, which is all northward movement, if we didn't do any northward or southward movement in between. And then finally, of course, D2 is what we did in that second leg of the journey, but that's what brought us west. So that's D2 right there, right? So I'm going to erase these arrows. We've got the size of our triangle. The size of our triangle, the northward side is D1 plus D3, and then our westward side is D2 by itself. All right, so now I'm going to remake that vector triangle, that sum vector, going from the start to the end. And that whole thing, again, we can make a triangle with our two sides, and one side is D1 plus D3, and then the other side is just D2. All right, so now we're going to try to add up those two sides. And so again, we're going to do this the same way that we've done this in the past. We're going to use the Pythagorean theorem, right? So c squared equals a squared plus b squared, not b cubed. And a is one side of our triangle, b is the other side, and then c is our hypotenuse, right? So really for our hypotenuse, we're looking for that d total that is that overall sum vector that we get in the end here. So that's our d total squared is going to equal a. Let's say that a is d2, that horizontal side over there. So this will be d2 squared plus b, but b is both d1 and d3. So I'm going to put that into parentheses, d1 plus d3. If we add those together, we get our b side over there, and then we got to square them added together, right? So our d total will be our square root of d2 squared plus d1 plus d3 squared. So let's plug some numbers in here. We'll take d2. The distance on day 2 was 7.8 kilometers. 7.8 kilometers, and it has to be squared. And then our distance for day 1 was 13.4 kilometers. So we'll plug that in for D1, 13.4 kilometers, plus our distance on day 3, which was 8.9 kilometers, 8.9 kilometers. So both those go in that parentheses that we substituted in for B. And then we're going to square them after we add them together. Oh, and I forgot an addition sign in between our two squared properties there, two squared terms. So we're going to plug that into our calculator. We got 7.8. Maybe my calculator is going to show up, maybe not. Cool, good, wonderful. There it is. All right, so we'll take 7.8. We're going to square that. Plus, I'm going to put in parentheses 13.4 plus 8.9. We'll end that parentheses, and then we'll square that. And then, so our total under the square root is 558.13. And we'll take the square root of all that, and we'll end up with 23.6. So our total distance was 23.6 kilometers. And of course, since all of our numbers had 3 sig figs, then we want to round our answer to 3 sig figs, which is what we did right here. D total equals 23.6 kilometers. Cool. All right, and then we'll take and let's go back to our graph we made here. I'm going to bring this down so we can investigate it in part B, because now, as usual, we want to take a look at the angle that we make from our starting point to our end point. And so right here, let's switch colors. I'm going to change on over to red. So if we started going north, then we are some angle away from north. We're going to call that angle theta, right? And just as usual, we want to think about our SOHCAHTOA, SOHCAHTOA, and we have every single side of this triangle, but let's use the two sides we were originally given, right? Which is we were given the sides rather than the hypotenuse of this triangle. So let's use D1, D3, and then D2, right? So we'll use our TOA because we know that tan of theta equals our opposite over our adjacent. So if this is the theta that we're looking at right here at this angle, then our opposite is going to be the D2, right? So D2 is opposite side. And then our adjacent side will be this side over here, this guy, which is again made of D1 plus D3. So we'll put that down there for adjacent is D1 plus D3. All right, and then we can plug in some numbers here. So D2, again, was 7.8 kilometers, and then D1 was 13.4 kilometers, and D3 was 8.9 kilometers. Oop. So our tan of theta equals 7.8 kilometers divided by 13.4 plus 8.9. So we'll do 7.8 divided by 13.4 plus 8.9. And as long as I put that addition in the parentheses, then my calculator knows to do that before doing the division, right? So that would be 0.34977. So our tan of theta equals 0.34977. And then to find theta by itself, we want to take the inverse tan of that quantity we just got. And so I'll go back over. Oops. We'll go back over to the calculator and we'll take the inverse tan of that. Inverse tan. And that should give us 19.2786. So our theta equals 19.2786 degrees. But let's round that. So that rounds down to about 19 degrees, right? And the answers, I gave you about 19 degrees here. I don't know why I gave you 19 degrees. Really, we should have rounded this to 3 sig figs since all of the numbers we were given had 3 sig figs, right? 13.4 has 3 sig figs, so does 8.90, and so does 7.80. So maybe really we should have rounded this to 19.3 degrees. And let's think about which direction that was. So again, we started from north, right? So if we look back over at our diagram over there, we started north and then we went east of that. So in an eastward direction. So this is 19.3 degrees east of north. We didn't have to start from there though. We could have started in an eastward direction. And then we could have figured out, well, how far north of that do we have to angle ourselves to get back to that sum vector that we're looking at, right? And again, that would just be, we made a 90 degree angle right here between, we need a 90 degree angle here between the north and the east, right? So if we add those two angles together, this guy, and then we can call this one alpha, they should add up to 90 degrees. So for our alpha guy over here, we want to take 19.3 degrees away from 90 degrees. So another way to say our angle, right, and we'll call this alpha actually. Another way to say our angle would be 90 minus 19.3 or 70.7 degrees. And that again would be starting east and then going north of that, going to the north of east. So this is 70.7 north of, oh God, I've been saying east the whole time. I meant west. That's my bad. Sorry, guys. One of these will be the correct answer as long as you're keeping your bearings of north and west correct rather than screwing them up like I did. Okay, final problem. of all of our summer work. We're on another hike. It's a 3-day hike again, just like question 3. But this time we're going to actually switch up a couple directions, right? So on day 1, we're going to hike 7.8 kilometers to the east. So I'm going to start in some direction. I'm going to go east. That's not east. Screwed up my directions again. We're going to the east. All right. So it's 7.8 kilometers, and that's D1, the distance over day 1. And we are traveling that distance from our start position. Great. And then on day 2, we travel along the eastern edge of the plateau that we're hiking around, going 8.4 kilometers south. So now we went down by 8.4 kilometers, 8.4 kilometers. We'll call that D2 for the distance we traveled on the second day. And finally, on day 3, apparently we were pretty tired, so we only went 3.6 kilometers, but we went 3.6 kilometers to the west. So now we're going to go the opposite direction of that first day, 3.6 kilometers. And that's what we'll call D3, which is our distance we traveled on the third day. All right. So this gives us an overall vector, a displacement from our start to our finish, which I didn't label end. And our vector is going to look something like this, right? Now, rather than looking like the vector that we created, oh, it got so messy, in question 3, where we end up with a really long vector because we added 2 of our days together because they were both going in the same direction. Now we end up with a little bit of shorter vector, right? Because now D1 and D3 are working against each other. So let's see how that plays out when we run our numbers here. All right. So really, we end up with a triangle here that we made where we have one side that has gone south and the one side has gone over to the east. Right. Let's see if I can keep my cardinal directions straight for this one. So I'm going to let us erase this little end guy over here, and let's think about what those sides are. Right. So the side that goes down south is nice and easy because that just is the exact vector that we went south with, right? So that is just straight up D2. But let's investigate what's going on with this bottom one, this guy that's bringing us over to the east, right? Because this one is not D1, right? These two don't match one another. They're not equal to each other. And it's also not D3 because this one doesn't look like it necessarily is the same size as that arrow, right? So let's figure out how we get this arrow from our 2 eastward/westward vectors, which was D1 and D3. So if we bring down D1, D1 looks something like this, right? It looks like this. We're going this full length of that rectangle. That's D1. And then D3, if we start at that position where we ended D1, we then go backwards, undo some of that, right? Is D3 right there. And what we're left with then is whatever remains. And what remains is this guy right here. And so what this is really is we take D1 and subtract out D3. That gets us this side right here, this side, the bottom side of our overall triangle right here, our overall D total triangle. So to figure out that side, we have to take D1, our initial movement in that eastward direction, and then subtract out D3, which was our final movement that we made back in that westward direction that undid some of D1's progress. And I got a little bit crazy with the colors. We're going to call this overall vector D total. We're going to put him in red. And then we've got our southward direction, which was D2, the distance of which is D2. And then we got our eastward movement, the distance of which was D1 minus D3, or we'll call that D1 minus D3. All right, cool. So now let's think about our Pythagorean theorem. So again, we've got c squared, our hypotenuse is going to equal a squared, one of our sides, plus b squared, one of our other sides. So we'll call c our d total, and that's going to be squared. That's going to equal a. We'll just call this our side a over here. We use d2, that southward movement as our side a. plus side B we'll use as this guy, which is D1 minus D3. So D1 minus D3, and that'll need to be squared. And then we can plug in some numbers over there. So D2 is 8.4 kilometers. We're going to square that. Plus, inside our parentheses, D1, which was 7.8 kilometers, minus our distance for day 3, which is 3.6 kilometers. And then we're going to need to square that as well. So let's plug this into our calculator. So we've got 8.4. Oh, calculator, where are you? Okay, cooperate, calculator, come here. There we are. All right, so 8.4, we're going to square that, plus in parentheses, so that we do the addition first, or the subtraction first, 7.8 minus 3.6, and then outside of parentheses, we will square what's inside. So we get 88.2. So our D total squared equals 88.2 kilometers squared. And then on the left side, we want to square root that. So we end up with just D total, and then we'll square root what's on the right side. So we end up with D total, our total displacement equals our 88.2 kilometers squared, the square root of that. And my calculator is not cooperating today. Come on, calculator. There it is. All right, so 88.2, and we will square root that, and that gets us 9.39148. 9.39148 kilometers, and that kilometer squared was, we took the square root of, so that leaves us with just kilometers. And if we go back, all of our numbers we were given were all 2 sig figs, so we should round this to 2 sig figs, and so we'll round this at 9.4 kilometers, and that is our distance, and that squares with what we were given for an answer over here. So finally, I'm going to redraw this a little bit. Let's take a look. I'm going to redraw this. It's a little bit larger. We got D2 is our side over here, and then D1 minus D3 was our other side, and that gives us our overall vector, which was D total, right? And again, where that came from was the first day we went some distance over to the east. The second day we went some distance down to the south, D2. And then the third day we went some distance back to the west, undoing some of our progress from D1 to give us a shorter side for our east to west movement in total. Okay, so if we want to find an angle here, we're going to start up here, and then we're going to end down here. And we want to figure out what our angle is. So let's start going south, and then we'll move over to the east from the south direction. So this is going to get us some bearing that is east of south, because we started south and then we went to the east of that. So it's east of south. All right. And to get that, we got to use our angle, our SOHCAHTOA, right? And let's again use our tan, because our tan of theta is going to equal opposite over adjacent. And those numbers we were originally given will give us our adjacent and our opposite things, right? So our opposite in this time will be D1 minus D3 is our opposite side, the side that's opposite of our angle. And then the side that is adjacent to our angle will be that side that is made of just D2. So we can plug in numbers from there, 7.8 kilometers minus 3.6 kilometers for D1 minus D3 divided by D2 was 8.4 kilometers. And then we can get a number for that. And we'll need our calculator. We'll see if calculator wants to cooperate this time. I think it is. Whoa. Okay. So we're going to erase that. I'll put in parentheses 7.8 minus 3.6 and those parentheses. So the calculator knows to do the division, or sorry, the subtraction before the division, and then we'll divide by 8.4, and that should give us 0.5. Whoa, 0.5. And then, of course, to get theta, we want to take the inverse tangent of 0.5. So we can take our inverse tangent. Inverse tangent of that gives us 26.565. 6.565 degrees. And let's round that to the number of sig figs that it makes sense for our question, which again, all of our initial measurements were with 2 sig figs. So let's round this to 2 sig figs. So that should be about 27 degrees. And again, this is 27 degrees east of south, right? Because we started south and then we went east of that. We could have also started, let me put a different color in here, could have also started going to the east and then went south of that to get over to our overall vector, right? And that would have just been 90 degrees minus our original angle, right? So this would be 63 degrees if we're going south of east. And those are both the correct answer. Just depends on where we're starting from, whether we start from east or whether we start from south. All right, thank you for working through those problems. So this is the extent of trigonometry that we're mostly going to be using for physics. We're going to use triangles in order to put together vectors, which again are physical, will represent physical quantities that have both a magnitude and a direction to them. And since they have a direction, we can't simply add their numbers. We have to treat them like sides of a triangle, and then we get to find the hypotenuse in order to figure out what the magnitude of those two vectors added together is. All right, so this is all just a preview of the sort of fun we're going to have in physics. So I hope those questions went well. If you have any questions, definitely hit me up, shoot me an email, and we can take a look at them together. All right, otherwise I will see you guys in class for our first day, and I'm looking forward to it. All right, toodaloo, and enjoy the rest of your summer.